Good afternoon, everyone. It's my privilege to introduce Professor Arup R. Bhattacharya, who is currently working in the Department of Mechanical, Metallurgical Engineering and Material Science, IIT Bombay, as a professor. Uh, we welcome you, sir, for this particular session. And coming to his brief biodata, Arup R. Bhattacharya has received his PhD degree from Indian Institute of Technology, Delhi in the year 2000 under the supervision of Professor Ashok Misra on structure property relationship studies on polymer blends. He then took up postdoctoral research position at Georgia Institute of Technology, Atlanta, USA, in the School of Material Science and Engineering. During that period, that is from 2001 to 2002, he has worked on carbon nanotubes based polymer composite fiber under the supervision of Professor Satish Kumar. Subsequently, he moved to Leibniz Institute of Polymer Research, Dresden, Germany, as a postdoctoral fellow and was working on the processing structure property relationship studies on carbon nanotubes based thermoplastic polymer composites under the guidance of Dr. Petra Porsche. In the year 2003, he moved to Indian Institute of Technology, Bangalore, as an assistant professor in the Department of Metallurgical Engineering and Material Science. He has published more than 80 international journal publications. He has guided 19 PhD students and who have also graduated, and for 5 PhD students are currently working in his under his research group. He has mentored a few postdoctoral students. One postdoc student is currently working under his group. Professor Bhattacharya's primary research focus is on polymer nanocomposites containing carbon nanotubes, graphene, boron nitride, and molybdenum sulfide. His H index, as you're already aware about Google Scholar, H index is 32 with total citations are over 5,200. That's a very big count, sir. He's serving as a professor currently in the department from the year 2012. Thank you, sir. Thank you for accepting our invitation and agreeing to uh, deliver a talk on polymer composites, nanocomposites of carbon nanotubes. Uh, the session would be for 1.5 hour, followed by quality, so question and answer interactive session of 30 minutes, plus or minus. So the virtual stage is yours, sir. Thank you.
Thank you so much for your kind introduction. And I would like to thank Professor Fanish for his invitation to deliver a lecture on polymer nanocomposites. So today the title of my talk is Polymer Nanotubes Containing Carbon Nanotubes. This is the work which I'm showing here is mostly two of my PhD students, but there would be a lot of other work also published by other PhD students, which I'm going to show. So the outline of my presentation is, I'll talk about a little bit on nanomaterials and what are the different classes of nanomaterials, what is their size and the shape of nanomaterials. Then I will come to specifically to carbon nanotubes. And then I will talk about what is the influence of, in this particular case, multi-wall carbon nanotubes on two polymer blend system. And this is very interesting because, you know, this blend, polyether, ketone, and ABPBI. ABPBI is, I will come to the structure and the full name. So this is the 80-20 blend. The morphology is mostly matrix dispersed. Whereas this one, polyamide 6,6 ABS, which along with LCP, liquid crystal polymer, At thermotropic liquid crystal polymer and multi-wall nanotubes, we have incorporated in polyamide 6,6 ABS blends. And the change in morphology is of high importance because we try to achieve some functional properties like electrical conductivity and mechanical properties and so on and so forth. And I will conclude my talk on perspectives. What are the different challenges still exist? Because this particular work, I mean, on polymer composites started way back in 1999. Only very few papers came up in 2000. And then the first one of my papers came from my postdoctoral research from Georgia Tech. It was also on liquid crystal polymer with a single wall carbon nanotube. It was 2002. So from 2002, so if you consider from 2000 to 2021, almost more than 20 years we have already uh, we have we are already in this particular field, and there are a lot of exciting issues came up, but still there are a lot of challenges which I'm going to discuss in the perspective. So let me spend little bit time on nanomaterials. So what are the different nanomaterials? So you might have heard about, and these particular different type of nanomaterials, starting from quantum dots, fullerenes, gold nanoparticles, metal nanorods, carbon nanotubes, nanowires or nanofibers, you know, and all these, and obviously graphene. Graphene is still a kind of, very exotic kind of, nanomaterial till today. And if you consider this particular, if you look at these particular nanomaterials, they can be divided into four categories. One is zero dimensional nanomaterials. Why? Because they are of spherical. And if you consider there is no length diameter, so it is a zero. So quantum dots are already, I'll come to the, their size factors also. So fullerene is also like that. Gold nanoparticles also like that. They are in the range of few nanometers. Now, if you look at the metal nanonodes or the carbon nanotubes, so one of the dimensions is much higher as compared to others. Okay, so which means their diameter, say for example, carbon nanotube, single wall carbon nanotube, the diameter is around 1.4 nanometer, whereas in case of their length is in the range of several micrometers to even millimeters. So their L by D ratio, which means the length over diameter, we call it aspect ratio, is very high. And that is why they are called as one-dimensional nanomaterials, because one of their dimensions is much order of magnitudes higher than their other dimensions. Whereas in case of the 2D nanomaterials, graphene sheet, they have two dimensions, because the third dimension is the thickness, is a one atomic layer. And this is also case of the nanoplatelets and nanoclay, where you will find that the length and the width, they are basically of several microns or several nanometers to micrometers. Their thickness is very small because of one atomic layer or few atomic layers. And this is true for three-dimensional nanomaterials. So we have liposomes, nanoflowers, dendrimers, and all this. So now I will just spend 1 or 2 minutes on that. If you look at the scale of these particular materials, where actually we are talking about, nanomaterials, we consider mostly where one of their dimensions is within the between 1 to 100 nanometer. And what are those materials I just discussed? It is fullerenes or uh, liposomes, graphene, carbon nanotubes, silicon nanowire, polymer nanoparticles, and where the other materials they stand. If you look at the human hair, which we can see by our naked eyes, which is much higher in dimensions in terms of the nanometer, which is 10 raised to the power 5, whereas an atom, which is like 10 to the power minus 1 nanometer. Okay. So protein is, DNA is 2 to 3 nanometer, the diameter. Protein is 1 to 10 nanometer. And virus, coronavirus, or any bacteria, then red blood cells, they are much higher dimensions. Now, what are the different applications already they are in the commercially people are exploiting? Uh, you know that energy technology, supercapacitors, battery, fuel cell, and solar cells, and so many of them are already in the form of commercialization, or already the product is already in the market, exploiting the nanomaterials. Similarly, if you look at the industrial, there are a lot of actually applications in terms of the catalysts, nanopigments, water purification, and the most important one, which I forgot to mention it here, that the automobile sector, where there are, polymer nanocomposite plays a major role. Eventually, different kind of membranes, that is also very important. Even in the food packaging and processing catalyst, this in terms of the food technology, it is already being exploited. Then electronics, a huge way, graphene, it is being uh, the research is going on, and in a big way, to develop sensors, data for data storage, lasers, quantum computing, and stuff. And the biomedical imaging, drug delivery, biosensors, everywhere these nanomaterials are being exploited, uh, and exploited commercially, I mean industrially. And there are a lot of startup, lot of industry they have taken up from the lab to the commercially commercial plant to produce or commercially produce these particular all these product. Now, what I'm going to discuss today, the talk is, as I told you, that the polymer nanocomposites containing carbon nanotubes. Okay. I hope that most of you or the majority of you know what is carbon nanotube. So it's a coaxially rolled graphene cylinder. Okay. sp2 hybridized carbon. And if it is the coaxial cylinder involves is only one, then we call it as a single wall carbon nanotube. Whereas if there are subsequent coaxial cylinders involved in a given process during the preparation, we call it multi-wall carbon nanotubes. But as I just mentioned, that the single wall carbon nanotubes, the diameter is in the range of 1.4 nanometer. And this is what is the most important thing, that the nanomaterials, because of these exciting or unique kind of dimensions, they face a major problem in terms of the van der Waals forces. So what happens when these nanomaterials or carbon nanotubes, the nearby carbon nanotubes, there are strong, they actually face strong van der Waals attraction between themselves, and they actually form rope-like structure or the bundle-like structure in single wall nanotube. This is what is the transmission electron microscopy for a single wall carbon nanotube. Whereas the whereas if you look at here, it is a multi-wall carbon nanotubes. Now multi-wall carbon nanotubes, I mean the diameter is in the range of 10 to 20 nanometer. So the extent of van der Waals interaction is going down, and thereby they don't form really the rope-like structure, but they definitely entangle. And this is what is the most interesting thing, and what we have to, in order to exploit the individual nanotubes, we have to overcome their rope-like structures, because ultimately whatever uniqueness is coming from the nanomaterials, in this case nanotubes, whether it is single wall carbon nanotube or the multi-wall carbon nanotube, if we cannot utilize them in the form of individualized carbon nanotube, then most of the properties will not be achieved. So here is a TEM micrograph of polycarbonate matrix where actually multi-wall carbon nanotube being dispersed, and the multi-wall carbon nanotube is basically in the almost I mean the concentration here is 5 weight% in polycarbonate matrix, and you see here that they actually form a nice network. And when you say network, which means that this is a geometrical, establishing a geometrical contact between the nanotubes. And so why this is so important or fascinating? Because polymers otherwise is an insulating material, most of the majority of the polymer, except the conducting polymers. So when you actually develop a conducting network, because these nanotubes, they are metallic like materials, but single wall nanotube also show some semiconductor like materials, but multi-wall carbon nanotube is predominantly, it's a metallic. So when they actually form a network three-dimensionally in the polymer matrix at a certain concentration, they form the electrical percolation threshold, which means that the polymer matrix, which is otherwise insulating, they convert, they transform to conducting composites. And this is where the functionality is coming from the nanotubes. There are so many different type of functionalities we are going to discuss shortly. Coming to the requirement of a conducting material, if you look at, we can talk about conductivity, DC electrical conductivity, AC electrical conductivity, I'll come back. But this is where is the guideline, where we talk about the volume resistivity, okay? So if you look at that unfilled plastics, I told you that the very high volume resistivity, and then you have antistatic compounds where actually there are 2 or 4 orders of magnitudes of lowering of volume resistivity, and or rather increasing that particular volume resistivity is going down, and ultimately you get a ESD compounds, which is the dissipative compound, and these conducting compounds where actually you get a value of 10 raised to the power -2 to -4 volumes ohm centimeter, and these particular, this is the requirement, if you would like to develop EMI or RFI shielding compounds. And there are a lot of work which is actually being carried out by the scientific community last 10 years to develop EMI shielding materials involving carbon nanotubes as well as graphene, as well as, there are a lot of other, it's not only a very straightforward thing, because in case of the EMI shielding, there are a lot of other interesting issues. I'm not going into the detail, but the major issue, what we are looking at, if you would like to develop EMI shielding materials from the polymeric material, incorporating carbon nanotubes or graphene, you have to achieve this kind of, volume resistivity, or one upon this, which is a conductive one. So uh, basically we talk about, now we talk about the theoretical basis of electrical percolation threshold. And I just mentioned that, in order to form this network, we need to know that, we need to know that what is the role of L by D, or the aspect ratio. So this particular plot, which shows the volume content of filler for percolation in terms of the volume percent in the y-axis, and in the x-axis, it is shown the aspect ratio. And what you are showing, what you can see here, that as you increase the aspect ratio, when the aspect ratio is high, you are actually achieving the electrical percolation threshold as per the Wahlberg's equation is much lower as compared to the carbon black, which is basically a three-dimensional colloid particles. Okay, so whether they are one dimension, whether they are two dimension, whether they are three-dimension colloid particles, the major factor here is the L by D ratio, because aspect ratio is the one which is governing to develop the network-like structure. Okay, so this is what I have just mentioned, that in case of the single wall nanotubes, how this diameter they varies for different grades of single wall nanotube. Multi-wall carbon nanotubes, in this particular case, this value is not the one. I really don't feel that 1.4. 1.4 is basically for the single wall nanotube. This should be between 10 to 20 nanometer mostly. So again, when we talk about the polymer matrix, the one actually at this stage I would like to mention that if you know about the polymeric materials, they are of long chain molecules. Okay, and these long chains, because of their long chain, I mean the very high length, uh, and or rather the very high molar mass and flexibility, they they coil, so which is their thermodynamically stable situation. So basically for the polymer chains, they are in a coil state. Now, in order to mix polymers and the carbon nanotubes, you either have to take a solution route, which means you have to take a good solvent where actually your polymer you have to dissolve, and then they will be under the shearing action, you can actually mix polymer as well as carbon nanotube, and then you evaporate the solvent and put it in a petri dish forming a film, so on and so forth. And there are some fiber like wet spinning fibers. They are actually made out of a process called high jet wet spinning process, wet spinning process, which is basically they take a polymer dope along with carbon nanotubes, or eventually you can make a control fiber other than carbon nanotube as well, and then they actually uh, make the fiber using a RAM based system. Okay, but what is important here in this schematic, that what I would like to show you here is that whether when you are mixing with the polymer chain, so these are the coiled polymer chains, and this is eventually carbon nanotubes are it is shown here as a this uh, black line. They are also flexible, but they can be very rigid as well. Okay, so it depends basically. So that is the reason it is been showing like this way, and and if you actually put a very small concentration, then either individualized tube or the nanotube bundle, they will be far apart. And when you increase the concentration, then you can see they are coming closer, and at certain particular concentration, they form a contact, geometrical contact. And this is what we are talking about, the electrical percolation threshold, which means that otherwise the polymer, which is otherwise insulating, will be converting to conducting composites at this particular composition. So it's a concentration dependent. But here I'm not discussing much about the rheological percolation threshold, which talks about that other than this network, there are actually two more network is present in these composites. So you have a polymer network, you have a polymer nanotube network, and the nanotube network. Okay, so here actually in rheological percolation threshold, we talk about the flow behavior of the polymer solution or polymer melt. That is also another way of preparing the nanocomposites, where actually you get that what is the how the flow properties like viscosity, storage modulus, all these properties are being affected by incorporation of carbon nanotubes. So before going into this thing, I am starting with the what are the challenges, So so far, actually, as I mentioned, that you will find a huge number of research publication which came out in different journals. You will find a huge number of patents, Indian patents, US patents, European patents, Australian patents, a lot of patents, a lot of industries are working in this particular field on polymer nanotube field. for different applications, definitely. But till today, the major challenge is how will you disperse nanotube in the polymer matrix by the conventional, industrial process. We call it a melt mixing. Okay. Here you need to look at macro scale dispersion followed by nanoscale dispersion. I'm coming shortly. Then how to assess them, the extent of dispersion of nanotube in the uh, polymer matrix, whether it's going to be optical microscopy or scanning electron microscopy, transmission electron microscopy, or is there any other way you can detect that whether the dispersion is good, bad, or worse. And then when this, particularly there are two components like polymer chain and the carbon nanotube, or in generally, this is in this case specifically polymer chain or nanotube, but in any nanomaterial with polymer chain, interfacial interaction, how polymer chain interact with these nanomaterials, in this particular case nanotubes. So one is dispersion, which is a major issue, and how to assess them, and third one is the interfacial interaction. Now, if you look at this particular thing, this particular slide, I have taken from my former postdoc mentor, Dr. Petra Pechke. She published a paper in Composite Science and Technology way back in 2011. And the figure which I have taken from our paper is just to show, in the left-hand column and the right-hand column are basically, these are the low magnification, these are the higher magnification images of three different types of tubes, multi-wall carbon nanotubes taken from different sources. This one is from a Belgium company, NanoSil. I'm going to use this same grade, NanoSil 7000. This one is from Bayer. Right now, they are not producing so far. They stopped their production long time back. They call it during that time, this was named as Bay Tubes, and this is from a Chinese company. Okay. Now, what you can see in the in the low magnification, that these are more like a stone, small stone. Now, if you go to very higher magnification, what you can see here, that no, there are actually web-like structure, entangled structure, and this is much finer here, and this is here much finer. Okay. So in the same magnification, you see, when you compare, you have to compare it in the same magnification, both low as well as the high magnification, which means that, in terms of the extent of entanglements, nanosil has the highest entanglement, Bay tubes in between, whereas these Chinese tubes, you know, their extent of entanglements is very low. And that is the reason you can clearly see that even if they are entangled, but you can see them nicely, and these are not, again, I'm saying these are as received samples, which means that it is not added to polymer matrix. Okay. Going next, yes, saying something, anyone?
Nothing,
No?
sir. You can continue.
Yeah. So if you actually look at this particular one, that what is the mechanism of multi-wall nanotube dispersion during melt mixing? So this is very interesting. That if you look at the initial one, which I showed, this is schematically drawn here. These are called agglomerates. Okay. So you get the nanotubes, and there is a pre-treatment surface functionalization. I'm not going into that. Even pre-treatment also can give rise to some kind of exfoliation, in a sense that there will be tubes, will be individual tubes will be coming out. But if you actually put these tubes directly into polymer matrix, what will happen, as a function of time, you will find that this kind of structure is arising. If you look it under transmission electron microscopy, and after a certain time interval, what they actually mentioned in this particular publication, again from the same group, Dr. Petra Pochke's group, they published in 2010, and they see that you get a network comprised of individual nanotubes. So it's a transformation from agglomerate structure to a dispersed structure, where actually nanotubes are dispersed. But what are the mechanism? What they say, that this particular agglomerate, it can it can be ruptured because of the shearing action inside the extruder, you know or it can be erosion dominant mechanism, where actually because of the shear, one tubes are coming out from this web. Okay, and it is in this particular case, this rupture is a rupture dominant mechanism is a fast process, whereas this erosion mechanism is a slow process, but it is a mixture of two, or the combination of two, which is taking place during the dispersion. Okay, and that is validated through transmission electron microscopic examination or observation, that at different times how these agglomerates, they are getting ruptured, or getting eroded from this particular network, from these agglomerates. But my question is here, today, because of the short of time, because I have something else to discuss, here I put a question mark. Actually, they generalize this particular schematic or the mechanism based on their experiment on polycarbonate multi-wall carbon nanotubes. But my question is that, is it true for any polymer matrix? And which is, at this moment, it is very well known that the extent, the way, the manner carbon nanotube being dispersed can be dispersed in polycarbonate matrix. It cannot be dispersed in polyethylene or polypropylene that way, because the surface chemistry is different, interfacial chemistry is different, interfacial tension is in some cases very low, in some polymer it is very high. When you talk about the difference of surface energy difference between polymer and the nanotube, so a lot of thermodynamic factors, kinetic factors, which are involved. Then the major issue is that even if they actually made this observation based on the three different types of tubes, they found that this particular this thing. But the issue is that eventually uh, you will get this kind of structure, but with lot of you know uh, lot of limitations, in a sense that during shear, in some cases you have to increase the extent of shear, and thereby you will be decreasing the L by D ratio, because the tubes will be getting shortened, you know, because of the intense shearing process. So this is why I raised here questions, and we may discuss during question answer session. So this is one of the this is why I raised this particular one. This concept is called double population in binary polymer blend. Before I explain this particular thing phenomenon, let me show you that this is called microcompounder, twin screw conical microcompounder. So this has a which you can see it nicely, that it has a conical one. It has a conical chamber. The screws are not shown here. And once you close this one from feeder, you actually incorporate both your carbon nanotubes and the polymer matrix. And there are temperature controller is there, and you can actually control the variation of the RPM. Thereby, you can actually control the how much shear you are going to apply on your composite melt, and you can also vary the time temperature. Okay, so, and this is what is the very important equipment from DSM Explore. Right now, this company name is Explore, and they have their head office is in Bangalore. Okay, Explore, and this Explore is actually this machine is getting sold by company. Venture Technology Limited. Venture, this is the company which they are housed in Bangalore, and they have, why this machine is very interesting or important for nanocomposite research, because you can actually process material anywhere between 5 cc to 15 cc. Okay, whereas the bigger extruder, you can do it from anywhere between 50 to 100 gram to like kilogram and more than that. Okay, what is basically double percolation? When you talk about the double percolation, basically we talk about that if you take in a binary polymer blend, so you take, say, for example, isotactic polypropylene HDP, in this particular case, polycarbonate polyethylene. In this case, it is polyamide 6 and ABS. In this case, it is, you know, uh, polystyrene PMMA. So these are all immiscible blend, by the way. So they actually form a two-phase structure. Now, can we selectively localize the filler in one of the phases, first of all, in a co-continuous structures or bicontinuous structures, which means that at some composition, when these polymer blend, they form, both the phases form continuity. We call it a co-continuous or a bicontinuous structure. Then what you can do actually, you can specifically localize in one of the phases. In this particular case, vapor grown carbon fiber, they have actually they were successful to actually do it specifically in the HDP phase rather than isotactic polypropylene. In this particular case, it is in polycarbonate. In this case, it is polyamide 6, and in this case at the interface. And there are different materials: carbon black, here it is nanotube, here it is carbon nanotube, here it is vapor grown carbon fiber. So what is happening, that, as I told you, that co-continuous structure is basically a kind of structure where both the phases are continuous. And now if you actually incorporate nanotubes in a sufficient quantity, or any conducting filler, any filler in a sufficient quantity, means where actually they form this geometrical contact, the percolation at that given phase, then you need half of the material, half of the concentration needed to percolate if you take just one matrix. So this is a conceptual approach. There are thermodynamic thermodynamic reason that why why the fillers can choose one of them. There are kinetic factors, and there are melt viscosity ratios. So these are the three factors that actually determine that where you actually can locate them, selectively localize them, whether they will go preferentially to one of them or not. And that precisely depend on even the filler geometry, that also has an important role, whether they can be actually, uh, you can organize them or selectively localize them at the interface. So already I have spent 40 minutes, I can see that. So now I'm starting with the system 1, which is a blend of polyether ketone and 2,5 uh, polypara benzimidazole. Okay, so this is a blend without this nanotube. This is already blend is prepared. First of all, these two polymers are manufactured by Gardha Chemicals, and they also have a product containing these two. You know, this particular blend without nanotube. I'm talking about already in the market for a long, long time. They have a patent. They have a US patent and stuff. Now, we started working with this company some 5, 6 years back, or maybe 7 years back, because this work we have finished 2 years back. So we thought of, incorporating some functionality into the existing blend system. Okay, and this is what I'm going to discuss, that how multi-wall carbon nanotubes can influence different morphology and other issues related to this particular blend system. And here are some exciting results I'm going to show. So morphology, rheology, electrical conductivity, and I'm going to show the dynamic mechanical properties of these blends also. Okay, so this is what is the polymer, polyether ketone, and you can see the melting temperature is more than 375. The glass transition temperature is 172 degree, okay, very high TG. Whereas in case of the ABPBI, it doesn't melt. It has a very high TG of 485 degrees Celsius. Now, what is the problem? Problem is the extrusion has been done at 420 degrees Celsius, which means at that temperature, ABPBI could be softened, but because it is, no, not even softened, because it is lower than the glass transition temperature, so they actually dispersed as a particle, okay? So ABPBI, because of this high glass transition temperature, it is very difficult to process, and thereby they have taken a strategy that, you know, if we melt, if you choose a processing temperature higher than the melting temperature of polyether ketone, and you disperse and you actually add 20%, 28% of ABPBI into that, it's a uh, it's a immiscible blend definitely, and it's a two-phase system. And I'm going to show you morphology also. So we started with the industrial grade of multi-wall carbon nanotube. I mentioned earlier from NanoSeal. It's called NC7000 series. And if you look at their structures, if you look at the structures, under scanning electron microscope, you can see it very nicely that how entangled these tubes are. You know, when you have not done any pre-treatment, you have just ultrasonication you have not carried out. It is just the as received nanotube characterization, okay? And then one need to characterize also the Raman spectroscopy, which is basically intensity versus Raman shape. This should be Raman shape, and where actually they show you three prominent peaks. And here in case of the carbon nanotube, these two are the most important one. So D band actually tells you what is the uh, defects involved in this given structure, and G band is arising because of the ordered graphitic structure. So it's a tangential mode vibration. How these graphitic planes, they are actually being agitated because of this laser. So when they are exposed to a given wave number of the laser during Raman spectroscopy, so you will find the two peaks. One is called D band, another is the G band. So this actually is an indication that if you take a ratio of D by G, and if D band intensity is higher than G band, then you can see here very nicely that actually D band intensity is much higher than G band. So which means there are a lot of defects are there. But if you see in case of if you sonicate in tetrahydrofuran, there is a basically, we could see that, this D by G ratio is decreasing, which means that ordered structure is increasing. Okay. And this is what we are going to discuss also. So these are the routine characterization one needs to understand. And there are a lot of physics involved in this. Okay. So again, some morphology. So these are the multi-wall carbon nanotubes after sonication. This is basically, I do not know whether you can see it. Very nice, transmission electron microscopy taken at very high magnification at 2 nanometer, very high resolution. You can see each of the walls. So you can calculate how many walls are involved here. So you can nicely see, and then you can see eventually you can measure the diameter of these particular tubes. And then here also you can see it. If you look at in the 100 nanometer scale, you can see the entangled network. So where actually you can actually see a rough estimate that where actually where actually you can see that how the entire, what about the length of the nanotubes. And if you look at the length of the nanotubes are several microns, I mean micrometers. Okay. So coming to the next, that this was prepared by industrial, commercial melt mixer, which is from Warner Flider Machine, ZSK. And this is also, a commercial, industrially used injection molding machine, because this is the machine extrusion you might have heard about. This is for the mixing, and injection molding is to make the product of a specific geometry. And in this particular case, we made a geometry of tensile specimens and a lot of different specimens too, because even the flexural specimens also, to measure the conductivity, measure the uh, mechanical properties, dynamic mechanical properties, so on and so forth. So if you remember that I have mentioned that one of the two challenges which I have mentioned is, you know, uh, related to the dispersion. Okay. Now, what you can see here, uh, the challenge is the dispersion and how to assess them. First of all, let me mention that these are the cryo cut samples, and the sample thickness is 20 to 30, 40, 50 to 70 nanometer of this slice, and it was being investigated under optical microscopy. Okay, and these experiments, actually, to be honestly, I do not have facility of the cryocard. This was done in Canada, University of Calgary. We sent the samples and they have done it. Now, if you look at, there are few features involved here. Okay, so if you look at the bigger ones, which are non-melted part, which is the ABPBI. Okay, these are the ABPBIs, and we have calculated that what is the diameter involved with these materials. But other than these black samples, whatever you can see it, because here uh, it is basically 1% nanotube, and here you can see eventually bigger agglomerate, of smaller agglomerates. So these black entities are the carbon nanotube agglomerates. Okay, so one can see nicely that, one can plot that what are the different, distribution of this, uh, distribution and the number average diameter of these multi-wall carbon nanotubes. So you can find out, that what is the distribution in different samples. Okay, so as you can see that this is the width of this particular distribution plot is little more than 5 micron, and here you can see even at 10 micron, which is at 5 weight%. So that is a increased agglomerates. Okay, but overall this number average diameter almost remain the same, because there are a lot of issues involved, because here the shearing process is arising because of the major two issues. One is related to, the melt mixing, which actually produces shear. But the second one is because this ABPBI does not melt, they also having, because of this friction, because of the shear, they are also producing, helping to break the agglomerates. Because otherwise, we found in other polymer matrices where actually we have incorporated 5 weight% of carbon nanotubes, the mean average, or rather the number average diameter, or even the width of this particular plot is much wider, and this value is much higher. So this is what, so basically this is one of the way to characterize that what is exactly right after mixing, what is the state of dispersion in your case. And then the second one we did for the same slice, we took it to, we took it, we examined under scanning electron microscope. And this is, I think, the A1 is related to the 80-20 blend, where you can see a nice, smooth surface, which is the ABPBI, which is not melted. And here is the polyether ketone phase. And you can see it, there are, and one can see nicely that, if I make it little bigger, even bigger, you can see here that there are white dots appearing. Okay, so which means the dispersion is really good, and these white dots are the nanotubes. Okay, and this you can see it much higher. when the concentration of nanotube is much higher. So they are, what you can see here from this particular image, that they are, first of all, again, this is a ABPBI phase, this is a polyether ketone phase, and you can see it here. Number of nanotubes increased, some of the agglomerates definitely there, but the dispersion is definitely very good, excellent dispersion. And that is why even under optical microscope also, you didn't see very high, big agglomerates. Okay. Again, we have done this is a very sophisticated experiment. Um, uh, Most of you are well known with the CT scan. Okay, this is what it is. It is X-ray microscopy or tomography we call, and we with the help of a soft X-ray source, you take this you keep your sample with a 2D detector, and you know the image would be constructed one after another. They actually do it slice over slice, and then they reconstructed the 3D profile. And what you can see here is a very nice one. you know this is, I think, a very nice one, 3D structure of this blend. And again, what we could see in the optical microscope, you can see it very nice, that these are more of a irregular shaped ABPBI, which is like 18 to 20 micrometer in size. And you can see here some of the nanotubes, okay, very small, because it is 1% everywhere in all these cases. But when it is 5 or 8%, you can see this number of white dots or white entities, it is increasing. And still you can see the number what you are getting from here is actually matching with your optical microscopy, or even the even the scanning electron microscope. So coming next, that what you can do actually, you can do a lot of things actually. So if you look at, so this is the 2D image, this is the 2D image, and this is the 3D image. And you can, again, as I mentioned, that you can actually plot it. And this is for your, if you look at these particular, these are the size of the ABPBI, not the nanotubes. And what is happening, that if you look at, even if they are going into this thing, going in extensive shearing action, it actually, there is a it depends. uh, Even in case of the 5% of the nanotube, definitely there is a breakdown of these bigger irregular shaped ABPBI particles into smaller one. Here it is much more, frequency is much more, whereas this numbers is coming, and eventually the intensity of these particular frequencies increasing in between. Okay, so this is what is very exciting here. I'm also going to show a few micrograph later on also. So now if you look at the transmission electron microscopy, so this is more like a correlation. You first look at under optical microscope, then if you have a facility to look at under, by the way, this X-ray tomography, because here the resolution is 1 micron. So any entity, so agglomerate should be nicely visible here. But the best thing is, when you talk about the nano level dispersion, nano state dispersion, then one must need to do the transmission electron microscopy. And as you can see here, this is a smooth phase. There is no nanotube, and all the nanotubes are basically, they actually are localized in the polyether ketone phase. And why it is so? Because the polyether ketone, while the melt mixing, it has been melted, it is much less viscous as compared to ABPBI, which is a solid particle. So there is no way they can penetrate, there is no way they can diffuse into this particular phase. Okay, because the temperature of mixing is 420 degrees Celsius, whereas in this particular phase, this particular ABPBI phase, it has a glass transition temperature of higher than 480 degrees Celsius. If you understand this, we have done all these, characterization just to understand the state of dispersion, extent of dispersion, how they form the network, so on and so forth. Okay, and then what is the properties. I'm not going into the detail of the melt rheology thing, but because it itself will take long time. But as you can see here, complex viscosity. So initially, when you have added just 0.5%, there is not much change in the complex viscosity, both at low frequency as well as mid frequency and higher frequency. And there is no change in this particular shape of this particular flow behavior. Whereas there is a sudden increase in the slope here. And this is what we talk about in the low frequency region. This is called the rheological population threshold, because otherwise why there would be a sudden increase in slope in complex viscosity. Okay, they can be, it's more like a low frequency Newtonian followed by shear thinning, but they actually change, and subsequently when you look at, there is a formation of yield stress, and the entire at 5-8% this particular flow behavior completely changes. And one can actually look at this, polymer chain dynamics, how, G prime is proportional to omega to the power 1, and G double prime is proportional to omega to the power 2. And you talk about this, terminal behavior, and in presence of the nanotube, as you can see, this terminal behavior slowly disappearing. And at here, we call it a completely jammed network, where actually you don't see any slope here. So these are the interesting things. And in terms of the rheological response, and uh, coming to the next, I would like to show, I'm not going into this detailed analysis how one can do this rheological population threshold at different frequencies, from storage modulus versus nanotube concentration, or even tan delta versus multiple nanotube concentration. So it is coming as close to 1 weight percent is the rheological population threshold. Then here it is the same. But what I would like to show you here is the following, that if you take only polyether ketone, which we have done it with the nanotube, not the blends, what is coming in terms of the electrical conductivity. Okay, so I'm not going into the detail of this thing. You can see here polyether ketone also very nice, even the same concentration of the nanotube, 5-8% of the nanotube. And there are some agglomerates, how they form this network, not really agglomerates, because in the nano level, so they form this small network here, and which are actually interconnected by, which are connected by the individualized tubes. Okay, and what you can see here is the following, that here, if you look at the DC electrical conductivity, it stays almost same up to 3 weight percent. By the way, these samples which we have tested are of injection molded samples. This is very important, that what is the type of the sample. If it is a compression molded sample, you will see much early electrical population threshold, whereas in case of the injection molded samples, you can see a much higher electrical population threshold, because of the skin core kind of morphological development. There is a different extent of nanotube dispersion in the skin and the core, and that leads to some mismatch of this geometrical network. What you can see here, most important is that here it's almost like one order of magnitude higher. So we don't call it as a electrical population threshold. For electrical population to happen, you have to actually show that at least there are 5 to 6 order of magnitude change, and which you can see here from 4 to 5 weight percent. So we will call it between 4 to 5. The composite is becoming electrically conducting, which actually we did the SE electrical conductivity, and then use the Jones-Shur universal power law, and then Jones-Shur universal power law, and then from here one can actually look into this actually power law equation, and one can actually get this sigma dc, which we have done it here. Okay, so I will come to your queries. Some of the queries are started coming, but I will do it maybe within once I finish this particular section, possibly before I start the second section. I will take a few questions. Okay, because otherwise it's going to be too heavy. Okay, so now I'm going to show you that the blend you are talking about. Now, 80-20 blend, as I told you, polyether ketone is 80% and 20% is your ABPBI. And what you can see here, it is between 3 to 4. Okay, so which is basically an improvement in terms of this electrical conductivity. I mean the 4 or 8%, whatever you are reaching the conductivity level, 10 raised to the power minus 6 Siemens centimeter, you actually achieve the similar order of magnitude in case of the polyether ketone multi-wall nanotube composites at 5 or 8% nanotube concentration. So there are issues related to morphology and so on. There are most important thing is, as you can see, that there are huge increase in terms of the storage modulus. These are the logarithmic plot, but in terms of, if you look at, this is the glassy region, this is glass to rubber, and this is the rubbery region. And this is where is the most important thing, that this, the black one is the one which is the related to your 80-20 blends. Okay, 80-20 blends, right? Now, if you look at here, this is very interesting that because this 20% is ABPBI and it does not actually melt, does not even soften below 480 degrees Celsius. So they retain the storage modulus, even at 300 degrees Celsius. Okay. This is the TG for polyether ketone, and it is actually, that is what is the most important finding for us. And this is where actually we obtain patent for different system. We obtain 3 Indian patents, 1 European patents, and 1 US patent is due, which will be coming in this month. That there is a huge increase in heat distortion temperature. And you can see it here that at 5% this thing, there is a huge increase in terms of the retention of the storage modulus even at 300. So mostly your service temperature is restricted here, okay, glassy region, okay, because you do not want that your product being deformed, you want to use it. But even at that very high temperature, they are basically they retain the modulus so high that which is a remarkable experience in this particular case. So we have done that. What are the reasons, what are the different issues related to that? We found that even the glass transition temperature of polyether ketone is not actually shifting largely. But what we could see here, you could see the peak is, so there is a damping issue where actually the storage modulus component tan delta is E double prime by E prime, where actually E prime dominates. And not only that, there is a broader kind of, this peak, and which tells you full width half maxima, which is much higher as compared to your blend, mid blend, and which is basically an indication that because you have there is a more dissipation, and there are polymer chains are being interfacially anchored with the nanotubes. They are interacting with the nanotubes. So that is how you cannot differentiate which one is coming from the pure bulk polyether ketone or the polymer chain which are interfacially getting interacted with the carbon nanotubes. So these are the most exciting one, and this is what is the more. There are some way you can analyze much better way what I was talking about. That if you take T max, T upon T max, you can do a lot of different ways. This tan delta analysis, and this is one of them. And this is the marked actually decrease of the tan delta peak, which shows dissipation. And how the energy will be dissipated here and the stress will be dissipated. This is being largely addressed by this particular this thing. So before I you know go to this particular section, you know, uh, uh, so can I take two questions which are already there? Because then,
Yes, sir. Sure, sir.
yeah, because already I'm speaking for 1 hour, so that would be, yeah. So
There's a question by Jivananda
yeah,
T. Uh, Can we do functionalization of MWCNT for better dispersion in the polymer matrix?
The answer is yes, but functionalization itself actually has a shortcoming. The reason is that when you try to functionalize, if you look at the structure of the nanotube, which I showed you here, there, it's a carbon. Okay. Now, when you functionalize it, the way normally people do in a harsh chemical treatment, that you put it into strong hydrochloric acid and the sulfuric acid and the nitric acid and a specific ratio, and you actually disrupt the, not only you are shortening the tubes, but also you are actually creating some defects in the sidewall. So what is the issue? Issue is that if you are looking for mechanical property enhancement, then yes, functionalization may be one of the better techniques. But if you are looking for electrical conductivity, increased electrical conductivity, then possibly functionalization of the best one, because you are losing the integrity of the tube, I mean the electronic structure involving the nanotube, and thereby you will lose, you will be, and you will end up with a much lesser conductivity.
Okay, sir. The next question is by Suraj Karanjikar. You can ask it orally. Suraj, are you there?
Yeah. So what he mentioned that ABP, as you said, for ABPBI will not be softened because of higher TG. So during extrusion, that does CN carbon nanotubes get damaged to some extent because of what is
Churning action.
What is churning action? I don't know. So anyway, what I have understood from the question is, yes. So by the way, I mean, uh, any extrusion process for any polymer, whatever you do, forget about the carbon nanotubes, there would be degradation of polymer chains. Okay, so it is known. So, say for example, any thermoplastic polymer you actually extrude for first time, there would be molecular weight determination, degradation from the virgin one. If we do to the second time, if you mix for the second time, there will be again molecular chain degradation. So it is known. And yes, there is definitely maybe some tubes getting shortened and so on and so forth. But this needs to be, if I have to comment on this particular aspect, that did you, if you ask me, have you seen that any degradation or stuff, then I would say no. So far, whatever experiments we have done, it is not sufficient enough to see, to actually evaluate whether tubes are getting damaged or not. Okay. Damage means, I mean, in terms of the length, there is a shortening. Yes, there would be definitely in terms of the shortening, I have no doubt. But what is the extent? The answer is I don't know. Is it okay?
Okay, sir. Any other participant?
Hello.
Yes.
Yeah, actually, if we go for solution mixing, then melt mixing is beneficial, sir.
See, let me answer you this way. First of all, this solution mixing normally, in general, polymer community, they don't like that way solution mixing. Why? Because of the toxic solvent. Okay. And the recovery of the solvent, that is a major issue. Okay. So
Yes.
whereas in case of the melt, if you look at the extrusion process, which is a very much commercialized, it's only a extruder which will extrude your, which will melt, mix everything. Okay. So melt mixing always preferable. And but there are certain processes, like say if you have to utilize polyacrylonitrile, okay, PVA, polyvinyl alcohol, there are a lot of such polymers you cannot, or eventually the liquid crystal polymers like polyparaffiniline bench bis oxazole, PBO, which is a xylon fiber. They are being initially, what they do actually, they uh, they after their polymerization, they are so they make a dope. We call it a dope. Dope means 85% is solvent, say phosphoric acid, and 15% of the polymer is there. And in that particular phase, in that particular composition, they form a nematic phase, which is a liquid crystal phase. And what they do, and if you look at the, and if you know, if you have seen this, if you don't know, that is also fine. It's more like a stone. You cannot process them by
Okay.
any way. So what you have to do, you have to take a wet spinning machine. Before that, you have to heat that particular dope for prolonged time period at temperature of 130, 140 degrees Celsius for 5 hours, for 7 hours. And then one can do this thing by a ram driven system where you are actually, with the help of the piston, you are actually pushing your dope through a small dia. We call it a spinneret, and you get a single filament or multi-filament depending on, whatever this thing. So this wet spinning process is very well known, not only for liquid crystal polymer but also PAN, where which is a precursor for carbon fiber. Okay, and which is worldwide. It is even India also. It is like that. But in a given my the answer to your question is very specific, that if I have a chance to exploit melt mixing, I will always go for that.
Yes, sir. Yes, sir. Thank you.
Yeah.
Any other questions? Okay. Arup sir, you can start with the second
Uh,
half of the
so,
sessions.
uh, so if you don't mind, even the participants,
Yes,
uh,
sir.
can I take just 5 minutes break and then I will start my second system? Okay,
Yes, sir. It's
is it
okay, sir.
okay? Yeah. Yeah.
Dear participants, kindly uh, be online. There's a 5 minutes break taken by the speaker. He'll be joining back in a couple of minutes. In the meanwhile, if you have any questions, you can post in the chat box. Hello. Yes, Satish Kumar YD. Do you have any question?
No, sir. No, sir.
Okay. Please be online. The speaker will join you shortly.
Can I start now?
Sure, sir. You can start now.
Okay. So,
Please switch on your video, sir.
oh, I'm sorry. Yeah.
Okay, sir.
So, before I start my second system, let me tell you that the first system which I have so far I was explaining or rather discussing, it is an industrial blend. Okay. And the entire process we have adapted the industrial process, and that is where is the basically challenge for so many systems. But we were successful, we are lucky to achieve that, and because of that we came up with a lot of patents. And Gardha Chemicals in Mumbai, they are actually considering it as for one of their upcoming products. So coming to the next system, this is another blend, polyamide 6,6 and ABS with LCP. This is the blend is named as Triax, which is also commercialized a long time back by Monsanto initially. But Monsanto, for a long time, they are not in this business. Right now, I do not know who is Lindsys or some other company. They are owning this particular blend, which is a blend of polyamide 6,6, ABS, and LCP. We thought that whether if we just incorporate nanotube in different ways, whether it's going to give us more functionality in the system. And mostly I'm going to discuss about the electrical conductivity, but also the hardness and Young's modulus as well. So this is what is the I do not know what happened. Okay, so possibly it has come later. Okay. So let me start with the fact that, this polyamide 6,6 and the ABS, we have taken 50-50. And uh, again, you know, again, if you look at the morphology of the system, so these are the neat blends. So we have studied through XRM, which is a tomography, and this is a fractured surface morphology from ACM. Now you can see here that here, even in the 50-50, where the composition is the symmetric composition and concentration is the same, you get a matrix dispersed type of morphology. Here you can see these are the ABS droplets, and this is ABS droplets. Some of the droplets, you can see it in a deformed droplet, which is basically a case of, we call it as a coalescence, because the droplets can merge, forming a bigger droplets or little irregular shapes. When you add 5% of LCP, this is a thermotropic liquid crystal polymer, Vectra, thermotropic polyester, thermotropic polyester, which is basically, once you do that, then you can see even more coalescence process. Okay, so more coalescence phenomena, and coalescence phenomena is like, it is dependent on the interfacial tension and a lot of other issues. And where you can see the along with the droplets, you can see there is a long fibrillary like structure as well, which is not evident from this particular ACM morphology. You see a bigger droplets, definitely bigger size of droplets, but definitely these kind of features are not present, which you actually see it in this particular side also. Now, coming to the what is the effect of this particular nanotube, what we have done, we actually kept LCP along with the nanotube concentration is fixed at 5%. So which means here it is LCP4, nanotube 1. Here it is LCP1, nanotube 4 weight percent. So which means total is the 5, and the nanotube concentration we have increased. What you can see it here, that this is what is the most extremely interesting one, that these samples are prepared by etching out specifically one of the phases in this particular phase, in this particular case ABS. We remove the ABS phase, and if you see it here, that instead of droplet, they actually form interconnected structures, more like a, so when you actually remove this ABS, what you can see it here is a hole, and the interconnected structures are the remaining structures which are polyamide 6. And you can see here that these are getting finer and finer and finer as you increase the nanotube concentration. So what is happening? So if you look at here, that initially these are the ABS droplets, ABS domains, which are basically removed from the entire surface, and then or the entire bulk media, and then they form a very nicely co-continuous structures in all these cases, and you can see it here nicely. You can see it here that their ligaments also getting finer and finer and finer. So you cannot differentiate here that basically, the structure is so fine that you cannot actually differentiate which one is the polyamide 6 phase and which one is the ABS phase. Even here also, in case of the SCM also, this is remaining one. You can see it here that the ligaments are smaller and smaller and smaller. But this is a qualitative way to say that, you can see with your naked eye that yes, this is the structure is getting finer. But what we have done, uh, we actually did analysis of the PS66 ligament phase by using the images software. And you can see here that at 1 weight percent, it was 6.7 micron, the polyamide 66 ligaments, whereas in case of the 5 weight percent nanotube, it is 4.7 micron. Okay. And you can see here, this is all our tomography images. This is a 2D image. This is a 3D image. So one can see nicely that how nanotube is refining the structure. And the reason behind this refinement is because that nanotube actually is altering the viscosity, or rather the viscosity ratio of the blend, which is the determining factor. Because nanotube being solid, they are, and specifically localized in polyamide 6 phase, they are increasing the phase, increasing the viscosity, melt viscosity of that phase, because otherwise ABS is much higher viscous than polyamide 6. Thereby, they are becoming close to 1, and the ratio is becoming close to 1, and thereby you get a finer and finer structure. Okay. Similarly, we actually have seen that what is the basically the polyamide 6, this thing. So you see the ABS ligaments, which is actually affecting much stronger way. At 1 weight percent, it was 7.9 micron, whereas at 5 weight percent, it is 2.3 micron. So you can see it very nicely that how these nanotubes, they are influencing the morphology of these structures. Okay, morphology of the structures, the phase structures, and you can see it very nicely. So this is at 1 weight percent, and all these samples are prepared, by specifically removing either ABS phase one time, and the other time it is polyamide 6 phase. Okay, so this is a better way of looking the morphology, because it's a 3D image we are getting, whereas in a ACM, scanning electron microscopy, the surface when you are looking, it's a two-dimensional morphology. Okay, 2D morphology. Now, if you ask me that, okay, what is the influence of nanotube if you just add it into LCP? Okay, so we did that, and we found that LCP, even at 5 weight percent, these LCP composites, even at 5 weight percent nanotube concentration, they remain to be insulating. Okay, so this is the DC electrical conductivity. There is almost marginally any change of conductivity, and we have assigned this particular, or we tried to explain by the fact that these particular thermotropic polyester, they have a much higher affinity towards nanotube, and thereby they are forming an insulating coating on the nanotube surface. So eventually at 5 weight percent they are connected, but because of the better interaction with this LCP, they actually form a coating on the nanotube surface, and there is not enhancement in terms of electrical conductivity. Okay, so now if we look at what is happening in this particular blend? Yes. Now you can see that actually, there is an increase from the electrical conductivity. There is a population between 1 to 2 weight%. Okay, so which is very, very interesting. And as you go on increasing the concentration, it is almost like 10 raised to the power -3, -2 in the Siemens per centimeter in that range. One can actually fit into power law, and one can see the, you can calculate the PC, which is exactly 1.5 weight%. Uh, you can do it nicely by fitting this power law equation. Okay. So coming next to the mechanical properties, so mechanical properties, we did nano indentation, and from nano indentation one can calculate the Young's modulus as well as hardness, and you can see here that this is at 0 weight% of nanotubes, which means the polyamide 66 ABS with 5 weight% LCP, which is like 4 GPa, and with 5 weight% of nanotube, where actually there is no LCP here, but here it is 1% LCP, 4% nanotube. You can see here that there is a progressive increase in terms of the Young's modulus, and it is reaching almost like 6 GPa. Same in the case of the trend is the same in case of the hardness also. So the message is that along with higher electrical conductivity, you are increasing the basically the conductivity. You are increasing the hardness and the modulus. Even in case of the I'm sorry, the last one is for basically the PS6 LCP, not with the blends. So this is I'm sorry, LCP with nanotube blends, nanotube composite, where actually the influence of a nanotube on LCP. So it is increasing both modulus as well as the hardness. Whereas in case of the blends, also you are seeing that what is happening in how does the force versus displacement plot in nano indentation plot in case of the 50-50 blends. In case of the 50-50 blends with LCP 5 weight%, in case of blends or composites with the 50-50, this polyamide 66 ABS blends, where actually LCP concentration is 4 weight% and the tube 1, and this is with the P or tube 5 weight% with the 50-50 blends. So this you can see it nicely that how nanotube concentration is influencing both the Young's modulus as well as the hardness, and along with the electrical conductivity. So this is where one can utilize this particular blend system. Now, there are questions which came that I did not discuss so far, that that because these are all carbons, which are true for the graphene also, the similar kind of challenges, one can use covalent modification, which one of the participants asked me that why don't we go ahead with the functionalization. But as I told you, that functionalization actually destroys the integrity of the tube by shortening the tube. So you are getting the tubes with lower L by D ratio, which is not mechanically, that would be reinforcement would be much less. And secondly, your electrical conductivity you have to compromise a lot. Whereas we have developed a lot of actually understanding, and in the similar line, actually this particular methodology is called non-covalent functionalization, okay, or modification of the tubes. So you will find a lot of literature where actually people use surfactants. Now, if you look at the structure of the surfactants, one end is hydrophobic. These are all CH2, 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 and the another end is hydrophilic. Okay, whatever, cation, anion, whatever. So, and the interaction with nanotube surface occurs mostly through electrostatic charge repulsion. Why? Because this is in the deionized water, they actually form these negative charges bearing all this hydrophobic tail, and you get a positive charge. So what will happen, because now ultrasonication, during ultrasonication, when you actually introduce this particular surfactant, then these negative charges, they will attract, they will initially go to the nanotube, and then nanotube bundle. And once they go inside, they found that, oh my God, I'm in the wrong place, because they started repulsion, because nanotube is also negative charge, and this is the negative charge bearing the moiety. Okay, so there would be electrostatic charge repulsion, and thereby you actually end up with the agglomerates to basically agglomerates to individualized tubes. There are also example in the literature where actually pyrene carboxyldehyde is being utilized, or these kind of molecules, where actually people showed that you actually establish pi-pi kind of interaction between this aromatic ring and the nanotubes, because these are sp2 hybridized carbon. Alternatively, we prepared a kind of modifier which is more like a surfactant, but not surfactant, because surfactant, because of the specific structures, they form micelle beyond the concentration. Whereas we prepared we came up with a compound where actually middle segments, and there can be n number of this kind of molecules we have prepared actually, where actually middle segment is the hydrophobic. It can be 4 carbon, it can be 6, it can be 8, it can be 10, and one end is not hydrophilic, they are organophilic, and the other end is more like a similar as of surfactants. So now, even if you increase the concentration of this thing, this is the sodium salt of 6-aminohexanoic acid. The purpose is the same, because once you actually put it into deionized water, they actually dissociates into whole negative charge plus sodium ion. And again, during ultrasonication, they will try to go inside the bundle of these nanotubes. And once they go inside, they found that, oh my God, I'm in the wrong place. So once they start electrostatic charge repulsion, what will happen? You come up with a individualized nanotube. And moreover, as compared to this surfactant, uh, this modifier or dispersion has a much higher thermal stability. You cannot use most of these surfactants during melt mixing, because they are lower thermal stability. Okay, pico you can use any type of carboxyldehydes, because of these aromatic rings, they are thermally more stable. But you can use these kind of modifiers up to almost like 350 degrees Celsius, which is a much desired kind of modifier, because most of these commodity, even engineering plastic, you can process it within 350 degrees Celsius. Secondly, this functionality is being added deliberately, because to introduce some kind of interaction with the polymer matrix. Because if it is a other than hydrophobic polymers like polyethylene, polypropylene, if you have polyamides, you have N groups, which are carboxylic group and the amine group. And this carboxylic group can form these, interact with this amine group, forming an amide. So what is happening, between the tubes, you have, so this is what is being shown here. No, this is what is being shown. Chain, there is the nanotube, and these blue things are of the these modifiers. Now when you introduce the when you introduce the polymer chains, they will interact here, depending on where the functionality is. So these modifiers, they will be in between your nanotube and the polymer chain, and thereby increasing the formation, increasing the better extent of interfacial interaction. And this is what is being established, not we postulate this is what is might happen, and this is what is being we actually we have gone through a lot of experiments where actually the zeta potential measurements, that is actually confirmed that there is a formation of electrical double layer around multi-wall nanotubes with net negative charges, and this is because of the long range electrostatic charge repulsion between the multi-wall nanotubes. So this is what is the scenario, so which is very, very interesting. And later on, actually with the help of my colleague with whom I'm actually collaborating in my department, Professor Ajay Singh Panwar, we did molecular dynamics simulation, and between the graphene sheet, actually we actually incorporate this different different number of concentration of this NaHA, and to see that how they are getting displaced, and we observed that that the graphene sheets have a negative electrostatic potential relative to bulk, and NaHA stabilizes graphene via long range electrostatic interactions. And this has been actually you know appeared online long time back, published long time back. We are coming up shortly with another molecular dynamic simulation along with experimental studies very soon. The manuscript is getting ready, where actually uh, uh, more detailed molecular dynamic simulation and more extensive experiments have been carried out in this particular direction. So there are some examples I have given that, we have published a very fairly good article in Chemical Physics Letters with polyamide 6 with NaHA modified multi-wall nanotubes. And if you are interested, you can go through. And here we showed that the NaHA modified multi-wall nanotube leads to a much lower electrical percolation threshold in polyamide 6 matrix. And this is also in the case where actually we did with the polyamide 6 ABS blends, which has been published in Composite Science and Technology. By the way, both these papers right now have a citation of 185, which is, this one is published in 2009 and the other one is published in 2006. And this is with the blend system and how nanotube is influencing the morphology, rheology, and electrical conductivity. This is the uh, emphasis of this particular paper. We also, this is where actually I would like to show you that this is where the interesting thing, that with NaHA modified multi-wall nanotube, we could achieve a very low percolation threshold of 0.25 weight%. Okay. And this is what is most interesting, in case of the polymer blends, that you don't need much of the nanotube to be incorporated. But yes, definitely you can see that when you increase the concentration, like T4 T5 means which are like 4% nanotube with the no 3%, this is 5 weight%, and of different ratios, okay, 0.25, 0.5, 3 weight%, and 5 weight%. These are 3 and 5, and these are 0.25, and another is 0.5. And you can see it that there is nicely the electrical conductivity is getting higher and higher as you increase the concentration of your modifier. And that actually tells us that because of this beta network like structure, and we also observed through in that particular paper, it is nicely written, nicely explain that why this is happening because of the double percolation phenomena, where actually nanotube being specifically localized in the polyamide 6 phase. So another example I would like to give you here, that here it is the polyamide 6 same blends, but we try to look at the different non-covalent modification. And this has published in, I think, 2014 in SES Applied Materials and Interfaces by Amrita Poikar. And she was a joint PhD student of IIT Bombay and Monash Research Academy, joint PhD program. And you can see from this particular one how these nanotubes are modified either by an NaHA or by PICO. I mean the pyrene carboxylaldehyde, and how this network structure develops. And it's a very nice one, nice paper. So if you have interest, you can go through this particular paper to understand. There is a lot of informations and a lot of explanations are provided in this particular paper in the same direction. So here you can see here that this is the message I am talking about, that this black is, if you just put nanotubes, okay, as a function of, so in all these cases, there are 5% nanotubes, and these are all simultaneously added. So we actually we also looked at the processing protocol, how the nanotubes will be incorporated in the system. Here it is 5% of nanotube is the black, in the blend. Now, it is the blue one is basically your NaHA modified multi-wall nanotube 1:1 as a function of polyamide 6 concentration, and this red one is your pico. So if you see that if you actually modify either by NaHA or by pyrene carboxyldehyde up to this limit, this is much better as compared to the unmodified one. I mean, the electrical conductivity is much higher, and which actually tells you that you are actually getting a debundled multi-wall carbon nanotubes from an agglomerated entity. And the mechanism being different in this particular case is actually because of electrostatic interaction, and in this case, pi-pi kind of interaction. So the next one, uh, maybe I will just give two more examples that we came up with a very detailed understanding. This is published in 2015 in Physical Chemistry, Chemical Physics, Royal Society Journal, and where actually we look at what is the role of organic modifier. My PhD student Joyita Banerjee, she has undergone this thing. And this is completely experimental, and we try to look at different structures, and we propose some mechanism that how this particularly deagglomeration is happening via this particular organic modifier. There is another, the last one paper I would like to refer. This is also published in 2015 by Srikant, MS Srikant. He is right now in working as an assistant professor in VIT, and he worked on a hybrid nanofiller system of carbon nanotube and the graphene. And actually here also, this paper talks about the crystallization, the more fundamental one, and the interfacial interaction. But he also found that eventually that, you know, if you modify the system, there are interesting things in terms of the electrical conductivity, crystallization, and, you know, eventually the dynamic mechanical properties, so on and so forth. So having said that, I am almost at the end of my talk, and where actually I would like to conclude my talk by citing one paper by Professor Shanat Kumar, who is a very renowned uh, polymer physicist, and he worked in recent times. He worked extensively on polymer nanocomposites, the physics of polymer nanocomposites, and he has raised some outstanding theoretical questions in polymer nanoparticle hybrid. And this paper is published in, published in American Institute of Physics. This is the link I have provided here, and what he has discussed that so far, what are the things could be achieved, could be understood. But there are so many things which we could not achieve so far. So what it is says that it primarily focuses on the outstanding issues in this field and is structured around 5 separate topics: the synthesis of functionalized nanoparticles, their phase behavior when mixed with a homopolymer matrix, and their assembly into a well-defined superstructures, the role of processing on the structures realized by these hybrid materials, and the role of mobilities of the different constituents, the role of external fields like electric, magnetic in the active assembly of the nanoparticles, and the engineering properties that result and the factors that control them. While the most is known about topic 2, which is highlighted here in the blue color, we believe that significant progress needs to be made in the other 4 topics before the practical promise offered by these materials can be realized. So this is what I was trying to address, that even if it's an almost like 20 years or more than 20 years, people are working in this particular field, but there are a lot of things to understood fundamentally and also from engineering perspective in order to be technologically relevant. Okay, so before I say thank you, I would like to acknowledge different funding sources and SAFE and CRNTS, IIT Bombay, uh, our department central facility. Here the first system, Dr. Aditi Kapadia, being a PhD student and the employee of Garda Chemicals, she carried out the work. The second system, it was carried out by Vivek. Vivek, after graduated, he right now he's an scientist in ISRO. There are few papers I have shown from Dr. Surya Sarathi Bose, who is currently associate professor at ISC Bangalore. Last year, he has been awarded the prestigious Swarna Jayanti Award. He is doing exceptionally well in this particular polymer nanocomposite with graphene, carbon nanotubes, and other things. Amrita Poekar, after graduated, he was working with the SABIC Bangalore, and then she moved to Bombay. Right now, she's working with an industry. Dr. Joyita Banerjee is also there working, and Srikant, I told you that he has been he's working as an assistant professor in VIT. Here are my group members. So I have mentioned that so far 19 PhD students graduated so far from my group. 4 of them currently working and 2 of them joined recently. So they will start their semester from 26th of July. And postdocs, 2 of the postdocs, they did very well, Srinivas as well as Dr. Ifshita Chinna. I didn't present their work so far. And currently Swati is working on hydrogels. And I have a huge collaborator, Professor Ashok Mishra, who was my PhD supervisor, and currently he's a INSA distinguished faculty in emeritus faculty at IIT Bangalore. Professor Kulkarni, Professor Panwar, Professor Shamazdar, they are Professor Mithun Chaudhary, they are my colleagues from of my department. Dr. Surya Sarathi Bose, my former PhD student, who is working as an associate professor in materials engineering department. Professor Kuruvila Joseph, IIST Trivandrum, Dr. Petra Pochke, who was my, and Satish Kumar, who was my, they were my postdoc mentors, but still I collaborate. Professor George Simon from Monash University, Australia, Professor Moinak Mojumdar, Monash University, Australia, Professor Wenlong Chang from Monash University, Australia. We have mentored a couple of PhD students, Dr. Prakash Trivedi from Garda Chemicals, and recently one PhD student, Dr. Deepa Khandekar, she actually awarded the PhD recently with Rajdeep, Professor Rajdeep Bandyopadhyay, jointly co-guided by us, and he's from Chemical Engineering, IIT Bombay. So it's basically now I need to say thank you to the organizer once again for inviting me, and specifically to Professor Fanish, and of course the organizer, all the organizers and the participants. Thank you so much. If you have any more questions, I'm ready to answer.
Participants, you can ask questions based on system 2 if you have any.
Sir, good evening, sir.
Yes, yes.
Have you tried with organic conducting polymers by blending with these polymer matrix like polythiophene?
Not really. We have rather, if you go to my Google Scholar, if you type my name, you will find that we have done some work with the conducting polymer, organic conducting polymer with carbon nanotube as well as graphene, unzipped graphene, to develop supercapacitors based on that. We did some work with the supercapacitor field, but not really in the similar field what I'm talking about. Thermoplastic with the conducting polymer, no, we didn't do that.
Because those conducting polymers are thermally unstable.
Yeah, that is one of the reasons. And secondly, you know, that conducting polymer with conducting polymer, because they do not melt. Okay.
Yeah, yeah.
So there's a difficulty, but people also did some work, but with a different kind of. You have to do solution mixing, so on and so forth.
Yes, sir. Thank you.
Yeah.
There is one more question from Vinod Kumar. You can ask yourself. Vinod Kumar.
Sir, good evening, sir.
Yeah. Yeah.
Sir, there is any possibilities of natural fillers blend with CNT, sir?
Okay, and any
Unless
biodegradable matrix available with good mechanical properties. Yes, there are a lot of work going on with PCl, polycaprolactone, then PLA, polylactides. There are a lot of good work, commercialized product available with what you are talking about, only carbon nanotubes or even natural biofillers. Not only natural fillers, I mean biofillers with CNT in combination with CNT. It has been studied for a lot of different reasons, and biomedical application is one of the major applications.
Any other questions? Okay.
Sir, which is that company use that machine, sir? Venture Tech.
Venture Tech,
Name of the company, sir?
Venture Technology.
It is
But
in Bangalore.
Venture
Bangalore.
Technology in Bangalore, they are basically the distributor or Indian agent for Explore. Explore.
Okay.
Earlier name was DSM Explore. Micro compounder. If you write in the Google that micro compounder, DSM micro compounder or DSM Explore micro compounder, you will get all the information.
What may be the cost of that instrument, sir?
Cost is very high.
Okay.
For a 15 cc machine, only that particular compounder cost close to 1 crore.
Oh.
1 crore.
Anybody is having that in Bangalore? I mean,
Bangalore, I do not know.
okay.
Because with Professor Surya Sarathi, they didn't buy this one. They bought the Hake one, which is cheaper
Okay.
in the ISC Materials Engineering Department. But Bangalore, who are who are having this, I don't know. IIT Delhi, there is one machine, and possibly there are some industries they sold.
Yes, sir. Thank you, sir.
Yeah.
Any other questions by participants? Dhananjay?
No, sir, no. I understand.
Okay. Dear sir, I have one question.
Yeah.
Being a coordinator, I want to ask one question.
Sure.
On a general note, for the fabrication of polymer nanocomposite,
Right.
how preferential localization is done?
Differential localization means?
I mean, preferential localization with respect to carbon nanotubes in the polymer nanocomposite.
You are talking about that polymer blends, what I have.
Yes, blends.
Okay. So that is basically, you have to first look at their surface tension between the independent components. Say, for example, carbon nanotube, the surface tension or interfacial tension value at room temperature is around 38 to 40 millinewton per meter square. Okay. So polyamide 6 or 6,6 in the range of 32, 34 millinewton per meter square. Whereas if you look at the not ABS, if you look at, yes, ABS also, it is like 23 to 25. Okay. Now, so the natural choice is where there is a lesser difference in surface tension, filler will try to, filler has an affinity to go there. But this is not the sole reason. The second reason is the viscosity. Filler will try to localize in that specific phase where the melt viscosity is lower, because the diffusion would be much easier, okay, during mixing. And the third reason is that how you are exploiting the kinetic factor. I mean, whether, say, for example, you actually mixed this ABS, not ABS polyamide 6 or 6,6 and the nanotubes altogether, but rather you are taking a two-step process where actually you are adding, nanotubes with the ABS, which means a bad phase initially, and after 5 minutes of mixing, you actually add uh, the second polymer, which is polyamide 6. So what will happen during that processing temperature? Now ABS will try, the nanotubes will try to leave ABS phase and they will migrate to the polyamide 6 phase. Okay. Now, if you know the timing of this migration or the diffusion time, you can stop your, the processing time such a way that they locked at the interface. So there are a lot of studies people are trying, people are trying to achieve, but not always. There are certain, you need to understand also the filler structure, filler network. Whether they are globular or spherical, whether they are cylindrical, whether they are platelet-like, those are the limitations also. But uh, but it is always possible to push them or localize them specifically in one of the phases if you know correctly all these factors.
Okay, sir. So on behalf of, I guess no questions are there
Okay,
from participants end.
can I stop share? Yeah,
Yes.
yeah.
So on behalf of Department of Mechanical Engineering, MSRIT Bangalore, uh, I being the co-coordinator, I thank Professor Arup Ranjan Bhattacharya sir for sharing his knowledge on polymer nanocomposites with carbon nanotubes, fundamentals uh, like significance of aspect ratio L by D ratio, then SWNT, MWNT, double percolation, and also sharing his research work done by uh, two of his PhD students. Thanks a lot, sir, for inviting her, for accepting our invitation and delivering a talk on nanocomposites.